transcript get to what they're
outsource that now. I'm just thinking when I got my garden grant, okay, typically a week maybe,
okay.
because that gives the company time to get the request, print it, mail it, and then get it to the college. Okay. But I don't assume anything.
Right.
It's not in my nature. So I would follow up to make sure that number one, they sent, and number two, and got it. Okay.
Right.
Especially since the food is kind of flooded now. Did you guys see the flooding?
Right.
Yeah, it's from the storm the other day. Yeah. I have some friends who were actually they're in Boyton. Oh, is it app? Okay, yeah. They were sending me videos of they're on the top of the hill looking down, and they're just flooding everywhere. So I think Walmart got flooded. Yeah. So, and I like things are gorgeous now. So you're going to go to app. I have my education specialist degree from Apple. So yeah. So after teaching for 10 years, I decided I needed to learn a little bit about teaching. So I got an education degree from app.
Okay. Yeah, I do. About 4 people that have graduated from there, and I know about 8 people that go there.
It's a good school. We went through in order to get into the program, you had to have at least a master's, because this was like, you have master's, then you have doctorate, and halfway across is something called specialist. So I didn't want to write a dissertation, so I just got the specialist degree, which is like everything but writing a dissertation.
Okay.
I'm too old. I don't want to write. I'm so close to retirement. I don't want to write a dissertation.
Yeah, I was just getting out of the e-grad that they have, and they haven't met yet. It's just it'll be the 4th, 5th, 6th. So,
A lot of colleges are now outsourcing that because we have so many federal laws that we have to provide by with your records that it's easier just to make sure that. So they'll hire a company who is accredited for doing that, and they handle all the security stuff.
right.
I mean, just
Makes
what
sense.
I have to do for Moodle is ridiculous.
Yeah.
But it's going to take all your time. But you're going to are you still doing computer science?
That's all work.
On range plane, is it going to be a programmer, assistant? Don't know yet.
Honestly, I want to own a business.
I have a couple of friends who are contract programmers. One is Patrick Woods, and he's IBM. And so he puts code in the IBM like RPG, and he writes code in it. What he does. Do you know the language? Okay, which makes web pages talk with other things. So there's a language called, okay, I don't know the language. Anyway, there's a language that's like PHP. What it does is it takes a mainframe, which is completely not internet friendly, and it converts it into web pages. And so what he does is he uses that language and he carries Java through the RPG code and through icebreaker language, and makes a mainframe become internet friendly device. Which is, I'm like, I didn't know you could do that. That is so cool. So Patrick's been doing that for years. I have another friend, John, who is a programmer in C#, which is IBM, Windows version of Java, and so a programmer for in enterprise research, ERP company, enterprise research planning. So what he does is he uses C# to take all these devices and make them talk to each other. And it's actually having devices talk to devices. So I'm like, God, you guys are so smart. Yeah, but they're both self-employed. And so what Patrick does is, because very few companies need a programmer to do that all the time. So what he'll go to is like, okay, well, we have a project. We want to take this company online, and then he'll go in and work for 6 months to a year with one company, and then when it's done, he's contracted to finish and go to the next job. So, and one of my other former students is an IBM programmer for casinos in Vegas. Most of the casinos run off of IBM machines because it's billions, millions of instructions per second, and so so he's like, and I'm like, that I'm not sure that would be something I would want to do, but it's fascinating that IBM runs most casinos.
Didn't even think about it.
Yeah, I didn't either. And Paul was telling us this, and I'm like, dude, really? So he's like, yeah, it's kind of boring being involved behind the scenes. And I'm like, okay, well, you're not on the casino floor. He's like, no, trust me, I'm not on the floor.
Share this and videos.
Now, are you booted up? We rebooted everything yesterday.
Video now. I'm gonna log in and we will get that doc.
Working now. So when you're here, what they see is they have 2 cameras in their room. They see what the small camera sees in the insert and the screen button. Okay? They see the PC on one screen and us on another screen.
Okay, not inserted.
Yeah, no,
Say 2 weeks.
yeah. What our screen here shows, they have 2 cameras showing. One shows Google and one shows English. And do you want the camera to show you at the desk, or?
Well, what I'm planning to do is do some problems, and on board,
Yeah.
we'll reference
That.
this thing.
Okay. Yes.
Morning. Did you guys get your chemistry stuff done for tomorrow? No. The chemistry project stuff. You're working on it? Do you have a lot left? It's okay, it's just a rough draft. Oh, that's good. It's due Thursday. Where do you find it?
It was right there.
Oh.
We're not right.
Hey, Elise, did you get your test? I said. Yeah. Okay. Thank you. No problem.
Could we see what's on the chem test actually? See what kind of stuff they put on it.
Well, this is just general chemistry.
It's okay, I wanna see it.
I don't know if it'll be in there.
I just have an idea. Heat density.
Abbreviation.
Yeah, isotopes. Combustion. This is not bad at all.
It's not. This isn't chemistry.
Okay, so let's go ahead and get started now.
This,
It's just a basic answer.
First thing I want to mention is on the first test, the redo test, for the take-home part, as you see, hopefully DC Davidson County, can y'all see the projector that shows the notes? So on that, I just wanted to mention that you should include, when you do that, you should include the graph to label it, to indicate to myself or whoever would be reading it, where your zero position is. That's important that you establish the zero position. The zero position, the two standard zero positions, again, are at the top of the cliff or the bottom of the cliff. But I mean, in physics, you can establish your zero position anywhere you want. You can establish your zero position at 10 feet below the height of the cliff, or you can establish it 100 feet above the cliff. That doesn't matter, as long as you're consistent throughout the problem with whatever you established and use that information. So you need to establish your zero position with a graph. Say, okay, my zero position is at the top of the cliff, or my zero position is at the base of the cliff. And put that graph on there. So clear? So I know where you're coming from. How are you solving the problem? Okay, then classes. We're gonna go over any questions you have, and then we'll do today's stuff. So, did you have any questions on the homework? Right now. Anybody have any questions on the homework?
Not like author 63. You really.
Oh, we didn't finish doing that one, did we?
Yeah.
Okay.
Yes.
Okay. So I guess we can finish that number one we were doing yesterday and see if that helps finish it out. So don't have to do like 49 to 63. Well, I guess go to the left board here. And what were we doing to start out? X to the side of X is, and then X goes to 0. Okay, this one we started on yesterday, and we said because it's got a variable in the base and a variable in the exponent, we don't have straight up rules that we can apply like so what we said, the plan to attack this is call this answer we're looking for. Just, the answer we're looking for is L. And so then I can apply the logarithm on both sides of the equation. And I can use properties of logarithms and get and then we observed yesterday that this is, so one more thing, let me back up just a moment, make a comment. Okay, so way back up here, I indicated that we had this variable base and variable exponent, but if you attempted to evaluate by plugging in 0, as x gets close to 0, sine of x gets close to 0, and that's it. So we end up with a 0 to the 0 power like that, which we learned previously that this was called an alternate determinant form. So that was back in a chapter or so ago. And then good job. But anyways, some time ago we talked about different types of indeterminate forms other than 0 over 0. And 0 to the 0 was one of them. So it's an indeterminate form from the beginning. And now by doing this, we're taking care of that problem. And now we're at the stage of 0 times negative infinity, 0 times negative infinity, which is also an alternate indeterminate form. Times. And then we rewrote it, and you can choose either way, but there's usually oftentimes an easier way. So not really in the numerator and 1 over x in the denominator is usually easier than putting 1 over log in the denominator. And then we did L'Hopital at this stage because if we check it now, we get negative infinity over infinity, which we determined yesterday was not an indeterminate form. That's just a standard indeterminate form. And the L'Hopital applies. Then we apply L'Hopital, and we get limit x approaches 0 of 1 over sine of x times negative cosine of times cosine of x over negative 1 over x squared now what? So I think we got to a point yesterday where we simplified this something like negative x squared times cotangent of x. And if we try to evaluate that, what you find out is that this goes to 0 times, and that's actually infinity. So we haven't helped a whole lot, but we at least got rid of the logarithm. That's a good thing. So this is still an alternate indeterminate form. So I need to do something with this. So I'm going to move over to the middle board now. Let's see. So what am I going to do? What if I write it as I'm going to try something now. Limit x approaches 0, and let's do negative x squared over 1 over cotangent of x. This statement here is equivalent to what we had over there. Dividing by the reciprocal of cotangent is the same as multiplying by cotangent. You all agree with that?
Mm-hmm.
Before I start doing limits or L'Hopital or anything else, what's another way of writing 1 over cotangent? It's just tangent. So if we analyze this by plugging in, we get 0, and as x gets close to 0, tangent of that 0 is 0. So this is a standard indeterminate form, and L'Hopital applies. So I can do a L'Hopital on this one. That's negative 2x over secant squared of x. Follow this?
Mm-hmm.
Now let's try to actually evaluate that. We use the continuity theorem. We plug in at 0. We get -2 times 0 is 0. And if you do the secant of 0, secant of 0 is 1 over the cosine of 0. Cosine of 0 is 1, so 1 over 1 is 1. So this is 0 over 1 squared, which is
That's where
0.
they're all 0.
However, yes, Rachel?
When it comes to deciding when to activate L'Hopital's theorem, does it have to be a standard indeterminate form?
It must be 0, yes, must be 0 over 0 or infinity over infinity.
And can it be like that?
Right?
Okay.
Must be
I was
one of those
asking-
two sequences.
Yeah. Okay, yeah.
Oh, you.
What's he saying?
Got something else, Rachel?
I just had a hard time understanding what you were saying because of the connection.
Okay, do you understand it now? Is it better now?
So I just need to, it's either 0 over 0 or plus or minus infinity over plus or minus infinity.
Correct.
Okay.
Those are the two options for L'Hopital. Any other form of indeterminacy has to be rearranged so that I can apply L'Hopital.
Okay.
So that's what most of this game was here. You know, I started off with an alternate indeterminate form, and I did some rearranging using logarithm to get out of this alternate form, way back over here. And then that got me out of this form, but then it put me into a different alternate indeterminate form, which is still not L'Hopital, but by a simple algebra gimmick, I changed this multiplication to a ratio, which turned into something that I can apply L'Hopital to. Then that kind of created a mess for me once I did L'Hopital, and still had an alternate indeterminate form, so I rewrote it one more time so that it's in a ratio form. And then I chose, instead of doing a derivative of 1 over cotangent, I decided to change the tangent from trigonometry, and that put me in a standard indeterminate form, which I can then apply L'Hopital to. So yes, the answer is, to do L'Hopital, you have to have it in one of two forms, 0 over 0 or infinity over infinity. Only thing I would say now is we're not done, because what we calculated way back over here, sorry, you switch boards from the calculus problem. It takes a lot of boards. We started with, we're trying to find this limit, and we called it L, but then we took the natural log of L, and then from this step beyond, all these equal signs are equal to natural log of L. So this isn't the answer, this is natural log of L. So therefore, L is equal to, how do you find L? What we've one more time. What we've determined is that the natural log of L equals 0. All of this work gets the natural log of L equals 0. To the 0.
Nice.
Okay, so that's how you're going to handle Justin asked, what about 49 through 63, every other odd, which I hadn't finished this one. All those are going to be kind of similar to that. You're going to have to get it out of the alternate indeterminate form with a power on a power. You have variable power on top of variable base. So to handle it is to, same game we just did here. There's logarithm on both sides of the equation. We'll create an equation by letting it equal to L. Let me try and find the L, which creates an equation. Take logarithm on both sides of the equation, and then at the end, solve for L by using the definition of log. Okay, any other questions? We'll try, I guess, try one more maybe or something.
You know, I'm gonna read it. Oh, same. I'm gonna read it right now. Okay, it won't take just about 30 seconds.
Reboot the sound.
Just the sound, not the
Okay.
system.
She's gonna reboot our sound since there's some difficulty now. While she's doing that, do you think of any questions you want to ask before we get started on today's lesson?
Stop talking everybody.
Brittany, did he cut off his lesson yesterday? What were we talking about? The logarithm thing? Okay, let's pick a question, guys.
Okay.
Disclaimer, you have a box of tissues in this room.
I have that before. I actually have tissues if you need them.
Okay, the sound, is it, yeah,
Is the sound better on your end now?
Yeah. Oh my god. Yes.
Okay, good. $37, I heard. I guess that should. Um, 37. Limit, so this is 37. Limit x approaches 0 from the right of log base 2 x over log base 2 of 3x, something like that. So what do y'all think?
You want to plug into 0 first to see if it's in a standard indeterminate form?
Yes.
Okay.
What do we get?
Wow. I don't know how logs work, man. I don't know how logs work.
The logarithm functions, even if it's a different base than e, are all alike, just like all exponential functions are all alike. They all have very similar shape and asymptote behavior. So yeah, that's negative infinity over negative infinity. That's correct.
Hey. That's nice. Are we gonna La Hospital it?
That is a standard indeterminate form and LH applies. So,
And Malcolm's favorite, and he's left-handed.
L'Hopital, don't, bless you, we don't do a quotient rule, we do a derivative, top derivative, bottom separately. So, the derivative of the numerator,
Fine. D over d of x of log 2 x times log 3 of x minus log 2 of x times the derivative of log 2 3 of x. And then all over.
wait, Rezo, is that you giving me the quotient rule?
Were you asking for the quotient rule?
No.
Or you want a L'Hopital hospital?
The L'Hopital, do a little hospital here, we're not doing quotient rule. So, we just need to do the derivative of log base 2 of x, period.
Okay.
So that's
What's that going to be?
What was that
log
again?
of x.
1 over x times natural log of 2.
Oh, crap.
Okay, good. What about the denominator? We have to do the derivative of the denominator separately. 1 over 3x,
Oh,
natural log
crap.
of 2,
Why times the log of 2?
times 3.
Because of the base.
Times 3.
I don't buy it. Oh, whatever.
Why are we
Where did the times 3 come from?
Was it a Hein rule? Is it a Hein rule?
Yes, the Hein rule.
Yeah.
Okay, so and you need the log 2 on both, natural log of 2 on both of them because this wasn't a log natural log. It was a different log base. So you need that multiplier to account for that difference. But then you needed this multiplier because it was a chain rule. Okay, now let's see if we can clean that up a little bit. Algebraically, we should be about done. So if I invert multiply, I get 3 over 3.
Oh. Oh, crap.
1 is
Look, that 1 equals 1.
Mm. Well, Mr. Gaddis.
is that right?
This,
Mr. Gaddis.
And we got a question here.
so if we multiply the 3 out, and then we get 1 over x times
Oh,
over x and natural log of 2, which is 1.
that's very simplistic.
Yeah, that's sure. You algebraically cleaned it up in a different order than I did, sure. Is that your question?
Can I'm a little slow. Can you demonstrate what you did between the second and the third step to get to 3 over 3?
Well, I see that there's a log 2 that can go away like that. Maybe I'll do it the way that Joe said it. I saw it a little differently than Joe did. I'll do it Joe's way. It's not one right way. Let's see. Instead of doing that, I'm going to say, well, it looks to me like those cancel. Then also this 3 and that 3 cancels.
Oh, that's good. That's good stuff.
That's 1 over
I did-
x over 1 over x.
Yeah, I like that.
I'll still get to 1 eventually.
Yeah, that's good. That's real good.
Either way, all right.
Yeah, it was fun. I enjoyed this class again. Oh yeah, we can ask that question. What was the number
All
you
right.
said?
Can you
So
go
we
over?
we need to. We have a question.
Can you go over number 23?
Number 23. Calculate each of the limits. Some of these limits are made easier by L'Hopital rule, some are not. Okay. So we'll go over here. Each of the 2x times 4 times 1 over x squared minus 4. 2x minus 4 minus 1 over x squared minus 4. X goes to 2. So if x gets close to 2, if I check this from the beginning, see what happens, then I get, let's see, 2 times 2 is 4 minus 4 is 0. E to the 0 is 1. 1 minus 1 is 0. And I'm going to plug in 2 here. I get a 0. So this is a standard indeterminate form, and L'Hopital applies.
The hospital.
So
We're never gonna give up that. Or the hospital.
I just have to do derivatives of the top and the bottom separately. Derivative of the numerator. Who asked for this question? I want to pick on that. Was that Chloe
Yes. Yes.
No, but
or was it Brittany?
it was
Who asked?
Brittany.
I couldn't tell. I could just hear a voice. I couldn't see who was asking. Brittany's going to acknowledge she asked. Okay, Brittany, how do we do the derivative of e to the 2x minus 4?
E to 2x minus 4. Is it 2? Is it e to the 2x minus 4 times 2?
Yes. E to the 2x minus 4 times 2.
You got him.
Okay. Minus 1 is a derivative is 0.
That's right.
Then what about the, well, the derivative of the bottom is easy. That's 2x.
Oh, shoot. Are we going to run the plug?
Yeah, let's apply a continuity. A continuity here. Run the plug, as I heard. What is this thing? That's definitely a new one. I've never heard it called run the plug. I substitute in 2 using continuity theorem. I have e to the 4 minus 4 is e to the 0. That's a 1, so I get 1 times 2 over 2 times 2. So that looks like a 1 divided by 2.
I dig it. Wait a second. 1 times 2
Is 2
is
over
2.
4.
2 over 4 is 1/2. Okay. Okay.
Yes. Or if I don't feel like doing all that arithmetic in my head, I can just cancel those 2's right there.
Oh, yes. Yes. We're good. We got it. We got another one.
I love his head shaking. He's just like,
Okay.
so I love this.
We're going to back up a step or two. That was section 3.6 on L'Hopital's rule. We're going to back up and cover
Watch us play.
section 3.2.
I didn't say
And we'll start that over here on this left board.
it wasn't all.
It wasn't
Good.
always this way.
It was like how much writing that was. But now it's out of order.
So, let's see.
We have to draw curves this time.
That's a lot.
And we'll start off by just giving you a curve and asking you to talk about it, analyze it a little bit first.
Hey, Brittany,
Yeah.
we're going to do my favorite thing in this section. We're going to analyze curves.
Okay, so there's a curve, a function curve. So this will be f of x. What I'm asking you to do now is, what would you say in the region to the left of this dotted line, this region in here, how would you describe that function curve? Think about it, to the left of that red line. The function is not always positive, but it is always increasing. Right?
Mm-hmm.
What would you say about the function curve
Oh, this.
between these two red lines? It's like it's decreasing in there. And then on the right-hand side of this red line, it looks like it's increasing. Okay. So what? what would you do for a derivative function? You had to draw a derivative function for this. How would you sketch the derivative function for this picture?
Well, it would be an increasing line at the beginning.
Well, positive line at the beginning.
Yeah, positive line at the beginning.
And so if it's increasing, then that means what about my derivative?
It's positive.
It's positive.
Positive. So
Yeah.
my f prime function has got to be positive, and then it switches to decreases. That means my f prime function needs to be negative. And then it switches back to increasing, which means my f prime function has to be positive. So f prime is greater than 0, f prime is less than 0, f prime is greater than 0. Interesting.
That's awesome.
I don't know. I hope it's not going to get too crowded, but I'm gonna draw another graph on top of that. To the left of that green line, what would you observe about the red picture? So the red picture is decreasing.
It's going down.
Over here, the red picture is increasing. So going back up here, what I was saying up here is that when I was saying increasing up there, I'm talking about F. So F is increasing, F is decreasing, and F is increasing. Now I'm talking about F prime is decreasing, and F prime is increasing.
Mm-hmm.
What would you tell me? Well, let's just go ahead and pick a graph. What would the graph of F double prime look like in green? So F double prime is the derivative of F prime, which indicates the slopes of the red function. So what would you draw there?
A diagonal line.
It's decreasing, right? So what does that mean? Which way am I?
Quadrant 3? Is that a...
So it's decreasing. Do I draw a line this way, or do I draw a line that way?
The
Yeah, I want
ladder?
to draw a line going up because the slopes here are negative, and the slope is 0 right there. So I want a line that looks something like this. So this is the graph. The green graph is F double prime of X. The red graph is F prime of X.
Just the squeeze. Get
Now I want to go back to purple.
it.
What can you observe about the purple graph on the left side of the green dotted line? What can you say about the purple graph? Well, it was increasing and then it was decreasing some. But okay, what else can you say? Well, you notice that on the left side here, the red graph is always decreasing. That means going back to position function, this is saying that my velocity is decreasing the entire time. So I had a high velocity, a little bit less velocity, a little bit less velocity, a 0 velocity, a little bit negative velocity, a little bit more negative velocity. So my velocity is decreasing that entire time. When that velocity is decreasing the entire time like that, we call that concave down.
I thought that was called deceleration.
What about to the right of the green line? On the right of the green line, the f prime function is increasing, so the f prime is now going up. What about the purple function? The right of the green line, our slopes were, before it, our slopes were getting more and more negative. Now they're getting less and less negative until they become 0, and then they become more positive. My velocity is now increasing. Velocity is increasing, so we say that f is now concave. Okay. To indicate that, we make sign, we'll call sign charts. If I put some numbers on this graph, you might be able to do some kind of sign chart, like let's call this number here negative 5, and that number there is negative 3, and that number is negative 1, and then 0. Let's make this number whatever 3, and this will be 6. If we use those numbers, we can make what's called a sign chart for each of those functions. F of x, draw a number line representing the x-axis, and I'm going to label the key points on the purple graph, which is -5, -1, and 6. So -5, -1, and 6, and then I'm going to put a sign above each region indicating what's happening on this function. So to the left of -5, the function is negative. Between -5 and -1, the function is positive. In this region, the function is negative, and then in that region, the function is positive. I could do the same thing with the f prime function graph. I could draw a number line representing the x-axis. I can label it with the critical points where the derivative is 0. So the derivative is 0 at -3 and +3. So I can label a -3, +3. And the derivative function is positive to the left of -3 and positive to the right of +3 and negative in between. So it's positive, negative, positive. And similarly, I could do something for the second derivative function. I could draw a number line, label it as x, and mark on it the critical point where it changes sign. It changes sign at 0. So at 0, it's negative to the left of 0 and it's positive to the right. All of that is a concise way to sum up all of the information we've seen here. This is telling me where the function itself is above or below the axis. This is telling me when the function is increasing. So it's increasing, decreasing, increasing. This is telling me when it's concave down and concave up. So we need to be able to read these number lines and sketch a graph from it. Okay? Let's practice that one time. So let's turn to page. I'm going to go to section 3.3. So my books right now, ladies and gentlemen, Dr. Jury, I'm arguing for both 3.2 and 3.3 at one time. In my books, those two sections kind of go together. Section 3.2 is on the first derivative, and 3.3 is on the second derivative. Well, if I'm going to graph, I'm going to do both of them at one time. I'm not going to just do one. So it's okay, the book broke it apart for us, but I'm going to turn to page 2. About page 275, number 54. Page 275, number 54. So we're given, and conveniently, they even use the same colors I did. Now that was not a plan, but I love it when it comes together like that. Wow.
That's your subconscious.
That's my subconscious one. Hey.
Really
Well, all along I've been using red for derivative because I draw my tangent lines for derivative. So that was just kind of the way I've always done. But hey, this author must be, pretty smart because she used the same colors. Okay, so number 54. F prime is a graph that I need to write here.
Computer code. They're from New York too.
So what they give us on that?
We gotta keep La Hospital, you know?
Lost.
We can't get rid of La Hospital.
54, they tell us that the sign, what they call the sign chart, F prime of X has this sign chart. What does it give us? -1 and 2, -1 and 2, and negative plus negative. Okay. It's a little similar to that, but not identical. And then we got F double prime of X, and we have a different double line, and it is at 0.5 plus and minus. They don't give us what F looks like, but we're supposed to sketch the graph of that from this. So what I'm going to suggest is kind of back up from where we were before. Based on this information here, at -1, something is changing. There's -1. And at +2, something is changing. It says that it's negative for F prime, which means that my function is decreasing over here. And it's positive for F prime, which means my function is increasing in here. And then it's negative, so that means my function is decreasing there. I'll put those numbers down here. So there's -1, there's 2, 0.5, so that's right there somewhere. There's 0.5. We have something else happening, so we're going to put a division here. And to the left of that division, it says it's positive. What is positive for F double prime mean? Positive means that positive for F double prime means that my slopes, my tangent slopes, are getting bigger. If I'm getting bigger tangent slopes, then I'm doing that. That's concave up. This is up. And if my derivative, second derivative is negative, that means my tangent slopes are getting smaller, they're decreasing. So I'm concave down. Now it's fairly easy.
Yay.
Sketching a graph. I got to be decreasing while concave up. That means I'm going down, but I'm starting to turn like that. So I'm coming down, but I'm concave. Not too purple. Coming down, but I'm concave up. So that's going to be decreasing but concave up. But then I've got to be increasing while still being concave up. So that means I'm doing this. Then it says I'm doing increasing, but I'm concave down. So now I'm going up and I'm turning the other way.
Oh, that's nice.
And I'm decreasing while concave down, so I'm doing this.
Okay. Mr. Gaddis?
Yes.
This is kind of reminding me of that antiderivative family stuff that we did.
Kind of. I mean, I'm not actually sketching. This is not a. It is in a sense. You're right. It is very much like because I'm thinking of negative slopes here. So I'm thinking almost like a slope field with a bunch of negatives, but because it's negative and then it's going to switch to positive, I know that I've got to change somehow in there. So yeah, it is like the slope field idea. I agree with you. Yes. Good.
And because we're not looking for a specific cousin.
Correct. Not at this point. We're just looking for this one. Now, when we get more information, like if I know, like over here, I knew x-intercepts, I knew things like that, I can be more precise. But for now, since this didn't give me any x-intercepts or any other points, you're right, I just get one big family of curves. So your answer might have been lower on the graph than mine, and it would still been accurate.
Okay.
Other things we would point out, this point right here, we would call that a local minimum. Is at -1, comma f of -1. This point up here is called a local maximum at 2, comma f of 2. And this point on the green change, so the local max and local min, we learned in 3.1. Those are your first order critical values that we talked about. Well, this one is a second order critical value. That's where it changes from plus to minus on the second derivative. That one, this point right here, is called an inflection point.
Yeah, that's what I was going to say. I remember it. You get PTSD for that first test.
The inflection point is where you change concavity.
Yeah.
Aiming up or sliding down, you're inflecting. So you're changing a concavity at the point, and this will be the 0.5, comma f of 0.
I think I have a cavity actually.
Okay. So that's sketching a graph from a sign chart. You're going to have to be able to do that. Given a sign chart or a group of sign charts, sketch a graph. You also need to be able to make a sign chart from a given function. So if I give you a function in algebraic, 905, let's look at time. I'll send out this concern algebra. I can't keep up with time classes. This class is 905, and other ones. I go until students start packing up. I'm like, oh, I guess it's time to go now. Okay.
Let's do it.
So what we need to do next is let's go over that. Is this still? Are you still projecting or sharing?
I haven't been.
You have now. Now let's share the computer and talk about this handout sheet that I put on Moodle for you. A note sheet about this. And we'll do an example or two. If we have, hopefully we have time to do an example.
Oh,
So this guidelines is summarized in the book as well. It's in section. I don't have to follow the camera here, but I'm just going to get the book real quick. So on page 267 and bottom of 267 and going over to the top of 268, the book has essentially this same information in a little different format. But I typed it up here for you. You can download this and study it if you like. So here's how we could graph, given a function f of x, how we would attempt to graph it. I laid it out kind of in steps for you. Step 1, determine your intercepts. So that's an algebra issue. That's not a calculus issue. Find your x-intercepts and y-intercepts. Y'all know how to do all that, right? We don't have to do that. Step, determining the asymptotes of the function. I even put a note that polynomial functions don't have any asymptotes. So if you get a polynomial function, skip step 2. Others have asymptotes. We'll see that. And there's a plan here for vertical asymptotes. And then there's a plan here for horizontal or what's called an oblique asymptote. If you used the word oblique before, some books call it a slant asymptote. So meaning it's a straight line, but it's got a slope other than the slope of 0. Oblique means going off at an angle. Okay. And there's a plan for how to attack that. We haven't done that yet. We're going to do that also. But for now, I just want to get through all this real quick and to do maybe a simple polynomial example, and then come back and do an example with the asymptotes. So then step 3, which applies to all of them, including polynomials, determine the intervals of increasing and decreasing. Well, that's what we just were talking about over there. We're doing increasing and decreasing. So we're going to find our first order credit values, which we did in section 3.1 by finding the derivative and setting the derivative equal to 0 or does not exist. And then you make a sign chart by breaking up into subintervals of the domain, and do a sign chart like we've done up here. And then you can analyze the function is increasing and decreasing based on the sign of the first derivative. Also identify local maxes and mins based on the sign chart. So in the sign chart, when we change, and I don't want to go there, but on the sign chart, when we change, think about a sign chart. If it goes from minus on the sign chart to a plus on the sign chart, what happens? So if you're a minus on the sign chart, meaning on the left-hand side of a critical number, it changes to a plus on the right-hand side of the critical number, what has to happen? You were decreasing and then increasing, so you had to have a local minimum in there. And if you went from plus on the left-hand side of the critical number and minus on the right-hand side, then it went up and down, so that must be the local max. Well, all that's just written out in here, so like it's not all that beyond what we've already discussed. It's just kind of putting it in a step-by-step organized fashion for you. If there's no sign change, then there's no critical point. There is a critical point, but it's not a local extrema. So we talked about that the day before as well. A critical point simply means that the derivative is 0 or does not exist. But on either side of that critical point, if it's a plus and then a critical point and then a plus, that means you're going up, you're 0, and then you went up. So that's not a maximum or a minimum. It's just a flat spot in the road temporarily. Or is looking at second order, so the second derivative, and it's the same thing again. You're doing the same process, except for now, second derivative tells you about concave up or concave down. But going through the process of step 4 is the same as going through the process of step 3. You're just taking a derivative and finding critical points and making a sign chart, and then using that sign chart to sketch a graph. And the last step, step 5, is to literally sketch the graph. And so the steps there are to plot all the points. So you've got intercepts, you've got extrema, you've got inflection points. You plot all of those points and label them. Then you plot any asymptotes, which if it's polynomial, there won't be any asymptotes. Then you, like I did up here, you separate into regions of increasing and decreasing, and separate into regions of concave up and concave down. But once you've done that, like I did up here, once I've got my regions and I've got a few points that are plotted, and I already know, it's just a matter of connecting the dots, and there's only 4 shapes that you have to worry about. I've already discussed increasing concave up, increasing concave down, decreasing concave up, and decreasing concave down. So there's only 4 basic shapes you got to use to connect all your dots in between the regions. All right, so let's do an example. I don't care. Can we do both or not? Yeah, let's leave it up, and I'll do an example over here on this board, I guess. Let me find a good example we can work on. We'll start with a polynomial, simple polynomial example here of some sort, I guess. Well, how about I'm going to go to page 276, and I'm going to take number 67, just because it's a simple problem for us. X cubed minus 2x squared plus x. Maybe I'll do it on the middle board because I might need more space. I'm gonna do the middle.
It's a millboard? It's the big board.
Yeah.
That's like Big Bird.
Okay, so let's see. Where's my? That's the way it's down so long. Okay, so what was it again? This was, what did I call it? 60? That was almost. I must have laid down something. What did I put?
Score? 67?
Yeah.
No, I stuck off the head on myself. What did I say? Number 67?
Yes.
That's what I called. What's the function for 67?
F of x is equal to x cubed minus 2x squared plus x.
Thanks, Chloe.
Things like that. Okay, thank you. So the first thing we want to do, according to the cheat sheet I gave you, is find intercepts.
Yeah.
Okay, so I'll do the easy one first. Y-intercept. Okay, you have to have a 0 for x and plug in a 0. So that's 0, 0. Okay, that was easy. X-intercept. How do I find x-intercepts? So x-intercept is going to mean that I have f of x equals 0.
Yeah.
So x cubed minus 2x squared plus x equals 0. So back out an x, I get x squared minus 2x plus 1 equals 0. So x times x minus 1 squared equals 0. So x equals 0 and x equals 1. So my intercepts are 0, 0, and 1, 0.
I missed this. This is so clean.
Okay, that wasn't too bad. Let's see. Next up, asymptotes. That was, if I'm following that sheet, I just did step 1. Okay, step 2. Asymptotes. All right, it's called over. No asymptotes.
Because.
Step 3.
Yeah.
Step 3 gets into the first derivative analysis. So that's going to involve doing f prime of x.
3x squared minus 4.
It's 3x squared minus 4x.
Plus 1. Got him. Weakest connects.
Okay. Oh, now what? I found the derivative, now what?
You want to analyze it?
We need to do what with it? Analyze it. Let me just scroll this back. We'll scroll it back up to step 2 here.
That's a good.
Step 3. Oh, step 3. Just a second. We'll go ahead.
Mason, are you going to write that? Probably.
Now we want to set f prime equals 0 and does not exist, so we can find the critical values. Now we got to find critical. Critical means f prime, that's first order critical, is 0 or f prime equals does not exist. Well, this is polynomial, so that's never going to happen over there. So that's an NA over there. F prime of x equals 0, that can happen. Let's see what happens with that. Does that factor? I think it does. 3x minus 1 and x minus 1. Is that the right factoring?
Yeah,
So
sure.
x equals 1/3
Yep.
and 1. So those are my first order critical value. Let's go ahead and finish analyzing that a little bit more. So let's go ahead and make our sign chart for X axis, and this is 1/3. 1. So now I have to determine the sign, the plus or minus sign of f prime in those intervals. How do you decide that? Over there we had a picture to look at when we did it the first time. And now how do I decide it when I don't have a picture to look at to begin with?
You're going to plug stuff in.
Yeah, plug stuff in. Eeny, meeny, how about pick 0? 0 is left of 1/3. If you plug in a 0 into that function, or this function, it's the same function, whatever you want to do. If I plug in 0, it looks like I get a 1. So that must be a positive right there.
That's awesome. Yes.
And let's pick another one. Eeny, meeny,
Do 2.
2/3.
Do 2. Do 2.
2, okay, do a 2. That's like, what, 4 times just 12, minus 8 is still positive, plus 1 is still positive. I'm going to bet this is negative, but we really need to make sure, because it could be all positive, but I'm pretty sure it's negative. I don't know, gosh, 2/3.
Can you test 1/2?
Half would be easier. 1/2 bigger than 1/3, so 1/2. That's 3/4 minus 2 is negative 1. What? Negative 5/4, and then plus 1 is negative 1/4. So that's negative. Okay.
I love this.
So what do I observe? I know where it's increasing and decreasing, but what else do I observe?
What, these little
That
lines?
point, since this point, 1x 1/3 is in the domain of that function, it's a point on the graph.
Whoa.
You understand? Critical values could occur when it does not exist. So it could be an asymptote or something like that. But this point is in the function domain, so it's a point on the graph. I need to find it, and since it's plus minus, then it's a local max. So I have a local max is at 1/3 comma f of 1/3, whatever that is. Someone can start working on that. And then I have this one shows me I was going down and then back up. So this is a local minimum at 1 comma f of 1. That one I can do fairly easily, I think. 1 minus 1 plus 1 is 1. 1 and 1 is 1. And then 1/3, whatever that is. So, because I'm running short on time, we'll skip that for a minute. What time is it? How much time? 1 minute. Okay. Well, let's quickly do the second derivative.
200 words per second.
So now we're doing the second derivative. F double prime of x. Okay. So that was 6x minus 4. That wasn't too bad. Then we're going to do the second order critical. So that means we're going to set f double prime of x equal to 0, or it also could be f double prime of x equals does not exist. And you need to show that you at least considered that. Don't just leave it blank, because it has to be one or the other for critical values. And so at least indicate I considered it and that it's not going to happen on this particular function. Here we get 6x minus 4 equals 0, so x equals 2/3. So if I do my sign chart, I got a 2/3 right here. This is a slope of positive 6, so that must mean it's negative and positive like that. And this is now a inflection point. So we have an inflection point at 2/3 comma f of 2/3. And if I put all that on a graph, I should be able to get some kind of a reasonable sketch real quick for you. I squeeze it in here. So we've got intercept is 0, 0, and 1, 0. So there's a 1 and a 0. And then we've got regions of increasing and decreasing. So we've got at a 1/3 right here. And then we've got at a 1. And this is increasing, this is decreasing, and this is increasing. Then we've got regions of, oh, and I've got some maxes and mins here. I got local max at 1/3, F of 1/3, whatever that is. I'm going to say it's right there. And then I've got a local min at 1, comma F of 1, so that's right there. And then I've got at 2/3, I got an inflection point, and I got a change in there at 2/3. So there's 2/3. It's concave down, and then it's concave up. And I have an inflection point at, we'll say right there. All those points again, I'm going fast because I'm out of time. And so my graph, what do we got? We got increasing and concave down. So it must be doing something like this, and then it reaches the max, and it's still concave down, but then it changes to concave up. Oops.
Oh no. Oh
What did you
no.
want me to-
Oh no.
When you plugged in for the local minimum, wouldn't f of 1 be 0?
Yeah.
Oh.
Yes. Thank
That's
you. I
what?
was like, yeah, that can't be. Thank you. Good catch. And then, so local minimum is at 1, 0. So there's my function picture. So I get to go fast. Okay, we're out of time. Thank you. See you tomorrow. You have some homework on Moodle, some of which is practice with sign charts and stuff like that. But then there's a few problems with signs where you need to go through the whole process. Okay, so try that out, and we will. Tomorrow we have a test scheduled for Tuesday on this material. So we have
It's not that bad actually.
4
But
days
that's
of preparation.
at least not that one.
Yeah.
Interesting.
So what now?
Have I done?
Can you get an exact bag for that?
Oh man.
About 2/3.
Oh yeah. Can you play James Madison for a video that I'm making? Can you play James Madison for a video that I'm making?
427?
James Madison was a delegate from Virginia.
What video are you making?
That sounds reasonable. I'm gonna go with it.
It's really funny, Brittany.
Do I have to see
I mean, this one is a little higher than that one.
You already recorded.
This one's at 0, so you're
Battle between Hamilton and Jefferson.
What?
You literally just stand there and push drugs in there because it's Stephen Hawking. But see, there's a. I'll explain it. It's there's a meta to it. Oh yeah, Miss Klinger. Do you know Miss Johnson's here right now?
She's back today. I mean, I know today is one of the days that she has classes like all day long.
Okay.
So I'm not sure exactly where she is.
I
But
should come with me so I can give her my peer review annotated bib stuff. I finally found it because I purged my room. Miss Klinger, my room looks like an insane asylum. I have notes just taped all over the walls.
Yeah, Razor's just like, oh, I'm gonna study for the test. No, I'm just gonna keep everything.
I mean, it worked actually. It was very helpful for me to see it constantly, and it's
There's
just
no
permeating.
wall room in my room.
I made a wall room. I'm gonna get a giant corkboard when I go to college. Just tape stuff all over it.
fine. Chalkboard would be cooler.